All right, welcome back. We are game 3001 in the summer 2021 semester at George Brown, and it's week one, part one of our broadcast. We are now live on YouTube as well as Zoom. And so this course is AI for games for the most part. Uh, Again, today we're going to be talking about kind of an orientation of what the course is about, as well as an intro to AI, what is AI, and some expectations and so on. Okay. So who am I? I'm Tom. I'm your instructor for the first half of this semester. The second half of this semester, it's going to be Alex, which I know you all know and love. He'll be online in just after the mid-semester break, so you'll see him around for the second half of semester. I'll be guiding you through the first part. So again, for me, if you don't know me, I've been kind of teaching for about 10 years now, I would say. And I have a passion for VR, and my master's is in VR security interactions. I like to play Dungeons and Dragons. I talk about that a lot, as well as other games. I'm definitely a gamer. Lately, playing Destiny again with my friends on PS5, so that's pretty cool. So what is this course about? It's a little bit about me. So really what we're talking about in this course is game AI. And this is kind of the schedule of what we're doing. So this is kind of a breakdown similar to what I've seen or I've posted up on Blackboard. We'll be using Blackboard as our learning management system as normal here at George Brown. And in our course information, this kind of these few slides which I posted kind of talks about our schedule. So let's talk about our schedule a little bit. So this week we're doing an intro to game AI. We're going to be kind of going over again some collision detection. We're going to set up our assignment framework, which I've almost got ready to post again. I'm going to post an update to the assignment framework, which is a little bit better in terms of how we're going to use IMGUI. This is kind of for this semester. The assignment framework has been built by myself and Alex and others. And what we're doing is we are updating it this semester so that next semester when we get together for physics, that you'll have a better assignment framework that it works for you. So again, working steadily on doing that. We're also going to be talking about the importance of Git and GitHub. And your first lab is really, let's get the assignment framework working. I'm going to talk about the assignment framework, and let's put your little example up on Git and GitHub. It's a real easy lab. I highly recommend you get to it and do it with me. If you already have a GitHub account, that's fantastic. If you don't, then I'm going to set it up so that so we do that for our first lab. So that's coming up, on the lab hour, which is starting today at 11. And I'll talk about the schedule for today as well in a bit. This whole first half is really about steering behaviors and pathfinding for the most part. So that's the part that I'll be covering with you for the first half. And you'll have a mid-semester test, again, just before the break. We actually do get a break June 28th this semester from the week of June 28th. Notice that the schedule that I've listed here is the week of. So the week of May 10th is where we're sitting right now. But our mid-semester test is the week of June 21st, specifically the entire week. So I'll give you a mid-semester test that you'll have that I'll give you on the Monday, and you'll have until the Friday or Saturday to complete it. I'll let you know more details as we approach that date. And then when it's going to be a true-false multiple choice test based on the PowerPoint slides that I've given you for the first 6 weeks of semester, including this week. Okay, so that's what's happening. I'm going to come back to this in a second, but more or less, again, we talk about steering behaviors and pathfinding for the first half, which is kind of I would say your baseline or your foundation for what you do in the second half of the course. In the second half of the course, we really talk about decision making. So this is where we ramp up in terms of difficulty, I would say. The first half gets you kind of oriented on the assignment framework, and it also kind of teaches you how to use the framework to kind of create your assignments. And the second half really tests your ability to create more realistic AI for your games. Okay, so that's really the scope. So second half, Alex will be hosting the second half, and he's great in terms of how he's going to do his stuff. And he can do it slightly different than me, but we are aligned in terms of we kind of wrote this course together. So you're going to see that this is, kind of a nice way. We're going to nicely segue from my teaching style to his, and I'm sure you've had Alex in the past. In terms of evaluations, there are going to be at least 10 labs in this course, but we're only going to count 8 out of 10 of them. So if you miss 2 labs, you're okay. They're each worth 2% of your final grade, all right, or thereabouts, okay, because it'll be obviously a little bit more than 2%, because we're only counting 8 out of 10. And they're weekly. So every week we get together, we do a lab, and then they're due by the end of the week on Sunday to give you a chance to complete the lab on time. Now, I recommend, as we're doing the lab together, and if you're following along during our lab hours, you just get the lab done then. I think that's the best use of your time. I don't think it makes sense for you to wait until the end of the week or the next day or whatever to get it done. However, I have to admit sometimes I go a little fast, and that's why I record the lab session so you can follow along. I also do recommend that you do follow along. You do your homework, you do the lab, because it's going to make it easier for you to do well in all of your assignments, especially on your mid-semester test and your final test. You'll understand more if you do the lab stuff, and it also gets you kind of primed for coding. I think it's a great practice on coding. We're going to cover a lot of advanced topics in this course, things that you perhaps have not had a chance to cover. And I think one of the challenges is when, with this course is that we cover things like pointers, we cover object-oriented programming techniques, and so on. A lot of different methodologies, even things like some programming patterns. So again, I recommend highly that you do your labs. Assignment 1 and 2 are the ones that you and I are going to be covering together in the first half, and Alex will be covering assignment 3 and 4. Notice that they have kind of descriptive names, so steering behaviors and pathfinding for me, and then AI sensing and decision making for Alex. And we have a final test that we kind of made. It says practical here, but that's to be determined. Alex may elect to make this a theoretical test, and it's totally fine, either one or the other. I think you're going to have a great opportunity to learn a lot, throughout this semester. One thing of note is assignment 1, steering behaviors, is the only assignment that is individual. Okay, so what does that mean? It means that you all have to do this on your own. Okay, there are no combining. You're not going to share with anybody else, and so on. And one of the things that we're also going to ask you to do is when you create your GitHub repositories, that you make them private. Okay, so you're not sharing your repositories publicly. And the reason for this is so that way we know it's your work. You're going to share your repositories with myself and Alex. First with me, and then with Alex afterwards. Okay, and I'll give you the links for all those things, and I'll put them up on Blackboard so you have that information. Okay, so private repos this semester, and we'll talk about how to do that. And then pathfinding, as you go into assignment 2, 3, and 4, there's group work involved. Okay, you can't do the assignment without joining a group, even if you elect to do it on your own. And I highly don't recommend that for assignment 3 and 4. I think they're meaty assignments that have a lot of detail. And if you want to do well, you combine with your group members to get them done. Assignment 2 will only allow you to work with one other person. but I believe assignment 3 and 4, we have some flexibility on adding up to three people in a team. So total team size is 3. And again, some people have tried to, for whatever reason, submit on their own. They're like, wait, I can't see the assignment. You won't be able to see assignment 2, 3, and 4 unless you join a group, all right? Ever. So please do that. In fact, I've posted assignment 1 and 2 already, and I've already posted the group assignment 2 groups already up on Blackboard. So if you know who you want to work with already on assignment 2, please join a group. If you join the wrong group, or if you need to be removed, you need to remove, or kind of let me know about that as early as possible, because you cannot remove yourself. You can only add yourself, just as a FYI. Okay, so groups are a little funky, and I know people don't like them, but it's necessary for what you're going to be doing this semester. So just letting you know, assignment 2, 3, and 4, group work, and you can't even see it if you decide to be a group of 1. You have to join a group, okay, no matter what you do. I will repeat this as we go forward, but I know people every semester say, I don't know why, Tom, but I can't see my group. I can't see my assignment. It doesn't exist. Yes, it doesn't exist because you haven't joined a group. Okay, so that is assignment, the breakdown of evaluations. And I just wanted to go over one more time some of those details up online. So assignment 1 actually is already posted and is due week 3. So I've given you assignment 1 already. You can start working on it as early as today. And the reason why we're posting it early is because it's kind of an intro. It gets you used to the framework that we've given you, the assignment framework, and it also is a fairly straightforward assignment in terms of details. And I'm going to go over the assignment details with you in a separate video. So after I do kind of my little talk, my lecture talk, at the end I'll stop recording and I'll record a separate assignment video just for you guys so that you can go through and know what the requirements are for the video or for the assignment step by step. And I'll do the same thing for assignment 2 when the time comes. So typically we release assignment 2 week 3. I've released it early, so you have a sense of what is going to be due, so you can kind of understand the requirements. So assignment 2, what's going to happen is I'm going to record the video around that time frame where I kind of explain assignment 2 in detail. I'm not going to explain assignment 2 today. All right, so that is kind of the breakdown of what's happening. Let's continue with a couple of other things. One thing to note is that because of COVID and our remote teaching, actually, I think, remote teaching in general, which is probably going to continue in some form or another, for a while, is what we do for academic integrity is we ask you to post an assignment video. So the assignment video is really you recording your screen with screen recording software like OBS. You can use whatever software you like. Would that make sense? Please, though, whatever you do not use your camera to record yourself, as an example, and your screen. Okay, where some people have done that in the past for whatever reason. They've used their camera and they've pointed it at I'm talking about your your phone. So you have your phone in your hand, and for whatever reason you're using your phone to record your screen. Please don't do that. That is not acceptable. I also don't need to see your face when you're doing your recordings. The recording will be your screen. You're recording your screen, and there's going to usually be some kind of a single slide that I'm going to ask you to put together on PowerPoint that basically says, here's my assignment information. It's assignment 1, which is steering behaviors. My student number is, my name is, here's my picture, here's who I am. Or I want a kind of a real image of you on that slide. So it's like a single slide, and it kind of starts off your video. That's how you normally do it. And then you kind of record, your demo. You actually demo your application. So your assignment 1, in order for you to get full marks, you have to demo it. And I'll talk about that when we get to the assignment requirements. So every assignment, you'll be required to do a video. Okay, just letting you know. And it kind of talks about that single slide right here. So if you have a partner, you and your partner have to be on that slide, and your student IDs and full names and all that stuff, the course code, course name, all that stuff in the assignment must be there. In order for you to get full marks, a couple things that have to happen. One, you got to demonstrate your app's functionality. You also explain your app's code. So when you actually go through your little application you're making for me for the assignment, you're going to say, here's the code. This is what I did to, or what we did to make this work, and so on. I also want, I need to hear you. So if I can't hear your video is useless. So please make sure I can hear your video and I can clearly see your screen. If I can't see your screen, and if I can't, hear your sound, or if it's very low, I won't mark your stuff. I'm just letting you know. All right. I know that's kind of some might sound draconic, but I need it. Right. I need you to talk about your stuff. So please, before you post your video and all that kind of stuff on YouTube, make sure that you can hear yourself. If you can't hear yourself, I can't hear you. So I need you to be able to be heard, and the video has to be posted live. All right, so please do that. The video on YouTube or Twitch or whatever you're going to use could be unlisted, and all I need to do is, if you're afraid of sharing it with everybody or whatever, it doesn't have to be public. It can just be unlisted, and as long as you send me the link, especially on YouTube, I should be able to see your video, no problem. Here's what I will not accept. I will not accept a video file. So please do not give me an MP4 that is 400 megabytes. I will not accept it. I'm not going to download it. I'm not going to mark it. And neither will Alex. Okay. It has to be a link, guys. All right. A link to your video, not a video file. Okay. Another note about videos, just to go on, is when it comes to your video quality, I don't expect you guys to be video editors. Okay. So you don't have to be a professional video editor or a photographer, or I don't need you to do lower thirds or an intro. You're not a YouTuber, none of that stuff. I mean, I'm literally just have to say something like, hi, my name is Tom. This is, my student ID is, and for the course code, so on. And for this assignment, which is steering behaviors for assignment 1, that kind of stuff. So you introduce yourself. You go ahead and do your screen recording, and that's it. I don't need to see your face other than the image that I see on your slide. Okay, so I'm going through this because every semester, for whatever reason, people upload files. They do all kinds of stuff that we've asked them not to do, and they get upset when the mark comes back and it's like, can't hear your video, so you've lost this many marks. We can hear it's very, very low. We can hardly see your screen. And all that kind of stuff. And the quality is very bad, or you didn't include a video, so we're not marking you until you upload something. And, I know that sounds, kind of tough, but, we need it, right? We need to prove that it's you, and it's good practice for you anyway to talk through your code and your technology so you understand it better. And it gives you a chance to practice what it would be like if you were in an interview. Someone asked you, okay, so tell me what you did here, kind of thing. So I think it's really great practice. So, and again, your first one will be for assignment 1, which is due 2 short weeks from now. All right, so that is your video. One other thing that we've done is for the labs, and if I'm going to go up on Blackboard here again, if you look at labs, there are these lab submission requirements. I want to talk about these because Alex and I kind of talked about them last semester when we were doing Game AI, and I want to bring them to you again. So it's up on Blackboard. If you look on Blackboard, this is where they are. So a couple things. If you submit the zip of your project, it must be named GAME3001, the lab number, followed by your last name and first name. Okay, that's the zip archive. And typically we need your zip archive of your project plus a link to your GitHub. It's a clickable link that works, okay? If you give me a link to your GitHub and it's broken or it's not accessible, for example, you didn't share your private repo with me, you get 0 for the lab. All right, so that's kind of something that's going to happen. All labs for all sections are due Sunday at midnight, right? So there's multiple sections here. Lab submissions link disappears at midnight on Sunday. No late submissions allowed because it's a lab. You're supposed to do it in class as it is. I will not accept things like email submissions and that kind of stuff. Remember that the lab due date is Sunday. There's got to be 3 screenshots. So labs don't require videos, okay? Labs only require you to kind of make 3 screenshots for yourself about the of what you're doing. So show me you're running code, and that is proof that you've kind of done it. It's your code, you're running it on your machine, right? And please make sure every lab has different requirements. Make sure that when I ask you to do something, I've posted the video, follow the video requirements, worst case. Penalties. If somehow your Blackboard submission is incomplete, you started it and you didn't finish it or something, it's going to be 0. Alex, as an example, may do things slightly differently. If you submit just the SLN file, you get 0%, all right? In other words, if it doesn't work or you post an incomplete submission or something, by the way, this is the same thing for assignments. If you give me an assignment as an example and it's not complete or the GitHub link is broken, I can't access the assignment, it gets a 0, right? Unless you resubmit. So please check your submissions. Like you upload it, try and download it. Does it work for you? If it doesn't work for you, it's not going to work for me or Alex. If you submit a zip file with the wrong naming convention, 50% off, right? That's what Alex and I agreed to. So please make sure it's created properly. If there's garbage files, and I've talked about this before, but I'm talking about it again with you. For example, anything, and I'll talk about it today in the lab. The first lab, what garbage files are, if you don't remember what they are, if they are, and you submitted something like 500 megabytes as a zip archive, no, it's not acceptable. If you're missing screenshots, right? There's 3 screenshots, 25% off, as an example for per missing screenshot. Okay, if you don't have screenshots. So that's a bad thing. Please don't do that. It's going to affect your labs. And if you're missing stuff in general, you're going to just be losing marks. So please make sure you get these done. I know this sounds like a lot in terms of detail, but really it makes it much more difficult for us, myself and Alex included, if you don't do these things. And so what we're trying to do is kind of set a structure for you guys up front, right? So that way when it comes to you making your submissions, it's a lot easier for you to get feedback and responses. Okay, so notice that week 1, lab 1, now it's sitting out here right now, but later on when we start our labs, it may be in its own separate week 1, as an example, labs week 1, and then lab 1 will be in there. And it says follow the instructor's lab directions in class, because this lab is really about GitHub and that kind of stuff. I'm going to be talking about that. Okay, so that is our lab requirements, and I wanted to kind of set all this up for you ahead of time so that you know. Any questions about the assignments, labs, or any other, do you have any concerns about anything that we've talked about so far before we get into the meat and bones of what game AI is, what AI is in general? And I'm asking this because I want to make sure that you guys are good. Okay, I'm looking at the participants panel. Guys, if you're in the participants panel, please rename yourself. I need you to rename yourself going forward. I'm taking attendance. First name, last name. If you've, thank you, Lyra. If you only have your first name posted on your Zoom meeting, please change it to first name, last name. Please do that now. All right. If you have another funky a name, for example, it's some kind of nickname or something, that is not the greatest thing. All right, so please make sure you clean it up and post your first name and last name. Okay, I'll let you guys do that in a second. Okay, I think most of you have done it. I still see a couple people. Chris, let me see who else needs to update that. I think that's really it. Thank you guys for following instructions. I appreciate that. Okay, let's continue. All right, so this is the first part. Okay, so now we're talking about what we're going to do. So we're going to be using this book by Ian Millington as where we got our information for this course. We've also put it together Um, Alex and I put it together in terms of kind of taking the information from this book and putting it into the course. So, do you need the book? I think it's a great book to get. Because it's a good reference. But most of the stuff that we're going to be talking about is going to be in the lab slides or the lecture slides anyway. Okay. Um, so again, what is the goal of the course is to teach you the process of designing and implementing intelligent agents. I think that's a great way of saying it. Or we also call them autonomous agents for your game. And that is really what we want to try and do. So, what is AI? Everyone's heard different things about AI. Generally, AI is about making computers kind of take a look at tasks that are similar to what we do, what humans do. Before I go on, sorry, I'm getting some questions about. Sorry, Vitaly asked a question. Need to submit the assignment so that you can run it on your Windows machine, right? Yes, please. So if you're using a Mac, I'm not supporting a Mac during this course or Macs in general, Apple computers. I can do it, but my framework the framework that we posted is only for use on a Windows machine right now. The other question I got is how to upload 3 screenshots with Git in a repo. The answer is yes, and I'll talk about how to do that. Actually, not in the repo, separately. You'd actually add the screenshot separately. Again, please, Chris and our new joiner, if you can all, Kenneth, if you can please change your name as it appears on Zoom. So it's your first name and last name for attendance purposes. Okay, let's continue. So again, we've heard a lot of stuff. Things like, is AI about making the next supercomputer that's going to destroy humanity? No, it's not. General, that's kind of like general artificial intelligence, which we are. I know people have thought about the singularity and all this kind of stuff. We're very far away from that right now. When you talk to AI scientists, if you will, they'll tell you that we have many, many steps to go before we get to something like that. And the reason for that is because it's like if you and I want to build a teleporter, right? And I'm going to put it to you this way. So you and I want to build a teleporter. How do we teleport something? I know this is kind of weird, but that I'm talking about it in AI. But these are the kind of discussions we're going to have, during our times. How do we teleport something? Well, we can. If you think about what we need to teleport something, is we need to be able to see the place that we're going. Okay. So how the heck do we see the place that we're going? Far away. Well, we have some kind of sensing, right? We need to be able to sense or locate the other location. All right, here's something. In order for us to teleport, what thing is teleportation? Well, maybe teleportation is us breaking down our matter and converting it into energy. Are we alive? Those kind of things. Are we going to go through some kind of portal? What are the technologies that are the foundation for getting us there? As an example, I mean, we can't just, somehow figure out teleportation all at once. It's going to take several steps and other supporting technologies, as an example, to make a teleporter. Maybe it's going to be to do with quantum entanglement. We don't know, right? How do you send energy? What about the differential between, where the Earth is to, right now in this second, because the Earth is moving, the universe is moving, everything is moving. How can I calculate where the Earth is going to be in the fraction of a second that I'm going to teleport you so that you don't go into the ground, right? There's lots of stuff that we have to talk about when we talk about teleportation. So too is general artificial intelligence. When we think about general artificial intelligence, you got to think about, for the AI to mimic sentience, if you will, or be sentient, there's so much foundational stuff that hasn't happened yet. Okay, not just natural language processing that we talk about today. Natural language processing is like, how we talk to Alexa, or when we talk to Siri on our iPhone or whatever, and they answer back and it kind of seems understandable. But most of the time they get it wrong, especially if you ask a question that they don't understand or they haven't been programmed to understand. So it's not true artificial intelligence or general intelligence. It's not like about that at all. It's something totally different. But what we're going to be creating here is we're going to mimic, almost like a player or an autonomous agent, so that they play similar to a human. Okay. One thing that computers are really great at, which is what we're talking about here in AI, is that they can surpass humans for calculations. They can calculate things very quickly. All right, so that's the advantage that they have right now. But a lot of times what we want to do actually is slow things down a little bit so that they make sense. We also don't want perfect AI, which we're going to be talking about, over the semester. If the AI is too good and presents too much of a challenge, or if they can outperform the human player all the time, it might become too difficult, example, to play the game. And if it's too difficult, you may not want to play that game anymore, right? If the AI is dumb, stupid, as an example, or it's predictable, that's another problem. So if you make the AI always do a certain thing, right, as an example. So if if a human player shoots a bullet at the AI, and every time they shoot a bullet, the AI ducks, right, as an example, and they duck in a certain pattern. We can predict. Humans are really great at prediction. We've got the best AI in the universe right now, as far as we know. And we can look and we can see that the AI is doing that. We can see the pattern. We can kind of predict what's going to happen and beat the AI, right? So if it's bad AI, then it's very predictable. And if it's bad AI, it's also maybe too hard or too easy. So these are things we have to adjust as we go forward. Other things to note is, what is the goal of you as an AI programmer? It's to make, AI seem more human by creating algorithms, okay, that allow, the autonomous agents to kind of display human properties as we go forward. So what we'd like to do is we create systems that think like humans. We can create systems that act like humans, but they're not really humans, and they don't have real sentience, okay, or intelligence. What they are is they're mimicking. They're presenting a challenge. They can be very realistic, and they can create the sense of immersion, which is what we're looking for in games, all right? The worst thing is, and I'm not sure about you, but the sense of immersion for me is always broken when the AI breaks, or if it glitches. Something happens where, I was playing Valheim last semester a little bit, and sometimes what happened is the boss monster, depending on which boss we're talking about, would get stuck. And when the boss got stuck, you could kill it pretty easily, right? And it kind of took the fun out of it. I like being challenged by a boss. If the boss is going to mess up, and I can kill it easy, so who cares? And one of the bosses that messed up for us when we were playing against it was Motor in Valheim. We just kind of stuck there. It's kind of a dragon, and it kind of sat on the ground the entire time. When we beat it up, right? It's supposed to fly around and attack you, but it got stuck. So if an AI gets stuck, it could be a glitch in the game. It could be a glitch in the AI. Sometimes it's a glitch with pathfinding. Any kind of glitches or anything like that, it breaks the immersion. If the AI is dumb, it breaks the immersion. And when the immersion is broken for us as players, we don't like the game as much, typically, right? Although some people like, if it's an easy boss to kill, they like that too. It depends on the kind of player you are. If you're a casual gamer as opposed to a hardcore guy or girl. So what about motivators? So again, there's a bunch of different kinds of motivations why we want to create AI. One of them is from a philosophical perspective. Maybe we want to study the nature of human thought. How does thought happen? Where is intelligence? Where does it come from? Again, as an example. So that's more of a philosophy perspective. Does intelligence come from our brain? Is it coming from the collective consciousness? What does it come from? Philosophy. There's also psychology, understanding, how a brain works. How do you make a personality? If I was going to create an AI personality, do I use a Myers-Briggs type of personality index or Big Five? What do I do to create a very similar psychology to a human being? And then from an engineering perspective, how do we perform tasks? How do I make an algorithm that mimics humans' performance? Those kind of things. How do I make a more convincing AI? Right? That's an engineering perspective. So there's different motivators to create AI. So, one of the things that we want to do is there's different types of AI, and one of the types that we think about is um, AI in academia. All right. So when we think about academia, that means like, in university and college, we think about doing research. Research is really the key if you think about becoming an AI programmer. And I'll talk about why that is. What we're going to be doing in this course is we're going to be really scratching the surface about AI. Okay, it's a first course in AI. It's an intro to AI more than anything else. It's going to give you a lot of building blocks, some foundational stuff that you can take away and make a really good game, especially from a 2D perspective this semester, because you guys are supposed to be tasked with making a 2D game in your Game Production 2 course. By the way, which if you're taking with me, I'll be joining you in the second half of semester. This first half, you probably have Philip. If you haven't completed your Game Production 2. So again, you're going to make a kind of a realistic thing, and the more realistic and more convincing the AI is, the more fun your game is in general. But when we come and let's take a look at the history of academic AI in a little bit, and there are 3 different eras that we should talk about when it comes to this kind of stuff. Again, this is I'm not going to gloss over the history too much, but it's good to know where AI came from a little bit. So there's the early days, the symbolic era, and the natural era. Okay. So let's take a look at the early days. So really, this began even before computers, came out. We kind of created mechanical models that were almost like clockwork models that kind of demonstrated animal-like behaviors. Example, clockwork machines. And I'm not talking about like steampunk clockwork. I mean, it really existed. There's things like dolls that acted very human-like, that walked around and so on, and that kind of stuff. They also even way back, they looked at things like what's the difference between, let's say, a cadaver, which is like a dead human body, and a alive one. What's the difference in terms of mechanics? How do we make what makes up a human being? So they started to look at those things to try and understand what is life in general. As an example, what is sentience? How do we get our stuff going? So the early days was really about understanding how do we have intelligence? What is intelligence? How do we define intelligence? And those kind of things. And pioneers like Alan Turing and John Van Neumann, Claude Shannon, they were kind of the early AI pioneers, around World War II and before that. Okay, so those are the people that were there. So here's this guy, Alan Matheson Turing. Again, he was around between 1912 and 1954. He was an English mathematician, as an example, and I know that there's been movies made about him as well. So we've got lots of really cool stuff. He was an English mathematician, a cryptanalyst, computer scientist, and so on. Some believe he was the father of AI, or the person who kind of created modern AI, or kind of jumped off with modern AI as it is today, right? He really formalized these concepts of what is an algorithm, things that we use today in coding. What is computation? What does that mean? So he kind of thought about those things and put them in writing. Again, we're talking about academic AI right now. And I remember back in my day, there was actually a language called Turing that we learned in university, to kind of kick us off. It was one of the first languages to kind of get an intro into programming. It was a functional language, and it was very interesting. We didn't really touch on object-oriented programming for a while. And again, back in my day, we learned assembly language, machine coding was our very first entry into how to code, or how to control computers, if you will. I think that's the proper way of saying it, as opposed to program. So what Turing did was he created a machine and called the Turing machine. That's a device that manipulates these symbols on a strip tape. Okay, like this is way before my time. Okay, and according to some table of rules, and really it was the first computing machine. Excuse me. And he authored a paper in 1950 called Computing Machinery and Intelligence, where he considered the question, can machines think? And the answer, I think, for me is, can we make them appear to think is the right thing to do? And I think that's the question that we're trying to answer in this course. Can I make a little AI agent that appears to think, appears to have some kind of behavior or can make decisions? And I think that is kind of one of the goals of what we want to try and do in the second half of semester. So he devised something called the Turing Test, and it came from a party game known as The Imitation Game. Okay, actually, The Imitation Game was the name of the movie about Alan Turing that was made. Very good movie. I recommend you watch it. It's very close to what happened. Again, based on reality. And the way it works is this: a man and a woman, they go into separate rooms, and guests try to tell them apart by writing a series of questions and reading the typewritten answers sent back. So that is the game itself. So, who is it? As an example, is this person A or person B? Who is it? And we're trying to figure out who it is. It's called the imitation game. And Turing's test, as an example, which really was, there's two players. A player A is replaced by a machine, and it's really up to another player to figure out if A or B is a machine or human. Okay. By the way, this is going to be on your test, your midterm tests, so you need to explain that. So, do we know if player A is a machine, or can we tell that they're a human? Can we tell the difference? And if we can't tell the difference, then we can say that the AI is good. We can kind of say that the AI is closer to being sentient, if you will, right? The interrogator is limited to using the responses to written questions in order to make this determination. So there's limitations on what they can do, right? As an example. But there were some critiques about this, the questions that were used, and how accurate, this kind of stuff was. Could you fool the Turing test easier? As an example, again, it was the first attempt to try and differentiate between a human and a computer. And if you couldn't, that's kind of a sign of artificial intelligence. So John Searle, he was another AI scientist, and he actually posted a paper called Minds, Brains, and Programs. And what he did was he attempted to prove that the Turing test was useless, right? And why? Because we can create, as an example, AI that behaves as if it understands Chinese. So the Chinese room. It takes Chinese characters as input, and by following instructions of a computer program, and then produces other Chinese characters, which represents output. And so here's his test. If suppose that the computer performs so convincingly that it is believed to understand Chinese, does it really understand? Or, and this is the key, is it simulating the ability to understand? And I think this is what we're going back to. It's simulating the ability to understand. It's simulating intelligence, as opposed to, and maybe that's what artificial intelligence should really be called, simulated intelligence, as opposed to general artificial intelligence or sentience, which we're very far away from. So really, he talked about two philosophical ideas that we're going to be talking about in this course. One of them is strong AI, and the other one is weak AI. Strong AI is machines would count as having actual minds. Okay, so again, very far away from that. And the other one, weak AI, the hypothesis is that machines could possibly behave intelligently. So most of the AI that we're going to be seeing in this course is most likely weak AI, because we're not going to make Skynet, in this course, or any course probably that you're going to be working on anytime soon. I'll put it that way. Okay. And the reason for this is because you're going to see as you start programming and try and make some of this stuff work, it's difficult. It's really difficult, guys. It's not easy to do. And in general, programming some kind of algorithm that mimics human behavior is difficult. So let's go back to the symbolic era. So that was the early days. The symbolic era happened from the late 1950s through into the 1980s. And so with the work that was based on Alan Turing's work, they created something called the symbolic system, which was one which the algorithm is divided into a set of knowledge, represented as symbols such as words, numbers, sentences, pictures, and a reasoning algorithm that looks at those symbols and tries to combine them and create meaning. Okay, and what it is the combinations are meant to represent some kind of problem solutions or even new knowledge. Because one of the things that they were trying to figure out is maybe the computer can come up with something that we wouldn't catch. We don't think, quote unquote, like a computer does. Again, I think that whole statement is wrong. Thinking like a computer does. The computer simulates thought. As an example, it calculates things, it computes things, but it doesn't think. We can create a quote unquote AI brain, but it's not really a brain like a human's. Frayne says, I already have problems the first semester without AI. I know, it's really tough. So an expert system is, again, the most famous symbolic AI technique. And an expert system is almost like, okay, the AI is created to mimic decision-making of a human expert. So they're trained to basically do what the human expert does. A good example of this is something like a chess game. If we program a AI to mimic an expert chess player, and they're going to do the same things that the human chess player does, it can appear that the AI knows how to play chess. But actually what they're doing is it's just following an algorithm. So, yeah, I think I've covered this pretty good. And then finally, the natural era. So that arose after the 1980s and into the early 90s due to a couple of issues. So early successes on some problems that were posed. AI could start to understand simple sentences. And when I say understand, I think the best thing is interpret. Okay, they were able to interpret simple sentences. So natural language processing started to come about during that time. But there is no breakthrough on entire languages, right? Now we're better. We're getting better and better at understanding stuff. But still, do they understand context? Like, does Siri or Alexa really understand what you're saying, or are they responding to an intent? A good example of this would be something like, hey, Alexa, what's the weather today? Kind of thing. And so what Alexa does is, look, actually, my Alexa is actually trying to respond, right? It's going to basically say, okay, so I'm calling out to the AI, right? Whether it's Google or Alexa or Siri or whatever. And then the first thing is it's responding, it's listening. Second thing is it's saying, okay, what is the intent? What am I looking for? What does the human want? The human wants to know about the weather. Okay. And then context, when, today, where, Toronto, as an example, right? So these are things that I can take and convert into symbols and stuff and say things like, okay, we want the weather in Toronto today. That's pretty simple to do, right? We can program an AI to respond to that. And that's kind of what natural language processing does. It takes a look at your sentences. It discards information that doesn't make any sense, right? As an example, any other language, anything in the language that doesn't make sense, that it hasn't programmed to do, as an example, and then only focuses on the words that it understands, and it tries to figure out the intent of the person and respond. Right? That's kind of the natural language processing that happens. Other things came out of this as well. neural networks, which we're going to talk about in the latter half of the course, and genetic algorithms, um, and a bunch of other stuff as well. Okay, so these are the things that have come out of the natural era from the 1980s into the 90s and even now. All right. Let's talk about game AI a little bit more in detail. So we talked about kind of like history of AI. Here's something. Andre says, I've tried to create an AI in Python, but that was like picture with dog. Yeah, I know, exactly. And what they try and do with that kind of stuff, with Python and we're talking about classification systems, is they try and classify what they see. Is this a dog? What's the percentage? What's the confidence that I'm looking at a picture of a dog versus a picture of a cat? What's the difference? What are the data points that I'm looking at as an example to discern the difference? In this course, though, we're not talking about necessarily classification systems, or anything like that. We're talking about game AI, and game AI started with as early as Pac-Man, right? I think Pac-Man was kind of the first really, I would say, popular, breakthrough with AI. I remember playing this back in the day, like in the arcade. And up to that point, Pong clones, all kinds of Pong clones existed with opponent-controlled bats, which are really interesting. And basically what they do is they follow the ball up and down, and a bunch of different shooters, Space Invaders, Galaga, and so on. And all those shooters and stuff, they didn't really have AI. They just had patterns. So if you could beat the pattern, as an example, you could beat the computer. You can beat the code. And some people had very, very high scores because they knew the patterns. They had great pattern recognition, and they learned the level. I died on this one level that was really, really hard, as an example. And Galaga, Space Invaders, those kind of things. You could kind of predict what was going to happen. Space Invaders actually was more of a game that it was see how long you can live, because now the Space Invaders were lower and lower, and they were getting faster and faster. It was kind of, in the beginning, it was an interesting game, and then afterwards became annoying as you played longer. Galaga actually had many, many levels, and you could have a crazy high score. But remember, back in the day, a lot of these games, even Pac-Man, were all coin operated. Remember, no one had a computer at home. So Pac-Man had some kind of interesting thing that the other games that when the arcade didn't have at the time, which was it had the ability for you to for the ghosts to predict where you were going to go and how they were going to chase you. So it relied on a very simple AI technique. It was a state machine, which we'll cover later on this semester in the second half. Okay, each of the four monsters, which were ghosts, occupied one of three states. Okay, they're either chasing, scattering, or frightened. Those are the three different states that the AI ghosts kind of went into. So they've shifted from one state to the other state, depending on where Pac-Man, kind of was situated. All right. So that's kind of how Pac-Man worked. So basically what they did is they chose a tile as their target, and they turned toward it at each junction. In chase mode, each ghost chooses the target according to a slightly different hard-coded rule, right? Giving them their personality. So really what's happening is, if I'm chasing you, depending on the distance that you're at or where you're going to go, if the Pac-Man or the player goes up in a particular part of the maze, then the AI will respond to that pattern that they're seeing by going in another way to cut the player off and so on. And of course, you could fool the AI, but by reversing direction, by going, kind of looking in different directions, back and forward, up and down. There was ways of fooling the AI because it wasn't really an AI. It was just a state machine that shifted the four ghosts from one state to the other. But it was really interesting the way it kind of worked. So that was the first one. Golden Axe. This is a great game. So again, mid 1990s. Again, I remember playing this one. I was fascinated about this because, like I said earlier, in my kind of introduction to who I am, I love Dungeons and Dragons. So when I saw this thing, Golden Axe, it was like, wait, I've got a barbarian, I've got a some kind of Amazon, and there's a dwarf. What? I want to play this game, you know. And so that was kind of the thing that that got me interested in it. And it had again, it happened like a bunch of years later after Pac-Man, and they're pretty much, you know, a little bit different in terms of the way it was. We had enemies that had a running state, and they also had something called a homing mode, right? And what they actually did was they actually came kind of attack you from behind, and they would work together in a way of to use pack tactics to defeat the player. Sometimes it was kind of very interesting the way it would work. And again, so a little bit more advanced AI than Pac-Man. Again, we're talking about we're in the arcade. On the console, again, this is a classic, and I would say that sure, for sure, Yusuf. Uh, uh, Here's something that is very popular, and it's been referenced many, many times. GoldenEye 007 was something that it had that was a lot different. It had this idea of sense simulation. We're going to be talking about senses in this semester. And let's think about the type of AI senses that are most popular now in any game you possibly can see. Even if you play a desktop game like Dungeons and Dragons, or if you play a desktop game like Warhammer 40K, as an example, any game like that, one of the main things that we want to talk about is something called line of sight. Okay, so I want to draw a line as the crow flies between the player and the enemy. Can the player can I draw a line between the player and the enemy, and there's nothing in between? If I can, then the player and or the enemy have something called line of sight or field of view. If I can see the enemy and they can see me, they can take action. So that's the first part of the sense simulation. And it's something that GoldenEye started with as well. So this idea of line of sight. Not only that, but other games like Thief, the Dark Project, and Metal Gear Solid had other kinds of sense simulations. For example, some kind of sensing radius. So, example, around the player or the autonomous agent, they could quote unquote hear the player or smell the player or sense the player in some way to make it more realistic. I remember also other games that we've seen, maybe a little bit more modern, games like Skyrim or Oblivion from Bethesda games, right? Where they would say something like, "Hey, I heard something. Did you hear that?" You know, and that's what the AI would say. And they would come towards the player. And if the player was hidden good enough, the AI would look around or have an animation to look around. I guess they're gone then. And then it would run back, right? And the problem with that is that, of course, you could fool the AI. Skyrim was one of the dumbest ones I've ever seen, or even, you hear that? Yeah, exactly. And then, you know, you use your bow and you shoot arrows at the AI's head in Skyrim or Oblivion as an example, and they literally show arrows out of their back or out of their head, and they're like, "Wait, where are you? You can't hide from me." And then they come at you as an example, and then of course you're hidden. You've got a higher stealth value than they can see, or you're invisible, and they're like, "I guess they're gone then," right? Again, an example of dumb AI, and there's a lot of other examples of that as well. Even things like Borderlands, you can't run away from me. I got you. I can see you. One of those kind of things. You're gonna die. The AI says a bunch of little things to you to appear to be human, to try and convince you. But at the end of the day, they're just following a pattern. They're just following a technique. Yeah. So there's so many of them, right? Like there's so many games, and I know Vitaly said a couple things, and there's a lot of memes definitely made up from some of these things. Took an arrow to the knee, and now, yeah. Let's continue. So when we think about AI, we can think about the task being split into three sections, or we can say levels. Okay, so the first section or level is strategy, right? And so what would the AI want to do? How can we detect? Detection for me is one of the levels as well. Another one is decision making. So, okay, now I've detected, I can see I've got some kind of interface that's input into my strategy. As an example, the strategy can be very simple, right? I make some decisions using some kind of mechanism, and then I move. Alongside movement, I may have a combination of animation and physics to make it seem believable for my autonomous agent, to act on the screen. Okay, so that's kind of the way it works, and this execution management system works every time, and it's kind of a loop, right? So every time, every frame, or again, actually, let me take that back. You wouldn't want to do this every single frame. Okay, so remember that frames are one frame is, let's say, typically 60 frames per second. We run at 16 milliseconds, 16.66 milliseconds. If you made changes to your behavior every frame, you're going to see a lot of jitter in the AI, because it's going to be like, okay, wait, I should go left. Okay, no, I should go right. Okay, the player's moving here. It's too much. So usually what we do is we add delay, 20 frames, 50 frames, 200 frames, whatever it's going to be before it changes. You let the AI do its action for a while, then change decisions later. And you need to tweak that as you go forward. The AI programmer has to find the right balance between realism and playability, right? So realistic, really truly realistic game, and then, but unplayable, right? So super realistic AI is hard to master as well. So what we want to try and do is we want to create this idea of an AI model or an AI agent. Okay, so when we think about strategy level, right, as an example, the only strategy level that, let's say, chess or Risk requires is that they basically have to think about the next move. What's the next move, and how many moves ahead do I have to go? There's different kinds of modeling that could be used, right? One of them could be predictive modeling, where I'm going to say, okay, so as an example, when it comes to let's say a board game, right? And let's even simplify it further. Tic-tac-toe was an example of a board game, right? Very simple. The first board game you can make anywhere you want, tic-tac-toe. And if an AI agent is playing tic-tac-toe with you, right, as an example, let's think about that for a second. What can they do? You play X on a 9-point grid, if you will, and they're going to play O to counter you. Well, they're going to know the exact position because they can, tic-tac-toe is a very limited game. It has limited amount of moves. It has a finite level of moves, right? So because there's a finite level of moves, and each state of the game is going to, every time we make a move, I make a move, let's say, and the autonomous agent makes a move, that represents a different state. And as we go forward, it becomes more and more finite, limited, if you will, how many moves are left, right? Because there's only 9 positions on the game board. And if you fill them all up, there's no positions left, right? So because we have this limitation in the number of moves that can happen, it's easy for the AI to predict and to win, or at least tie every single time, right? It's almost unbeatable. You can make a very simple, unbeatable AI when it comes to tic-tac-toe, right? Because it's such a simple game. Not so with chess. Chess has many, 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 many moves. And I mean that, like thousands and thousands of possibilities for every game state. And because of that, it's more difficult for the AI to predict the end game from your first move. It's impossible. In fact, it's so difficult, and it's so much calculations. We don't look that far ahead with games like chess or even Risk, right? They might have a strategy. For example, Risk might take a hard-coded strategy for different kinds of players. More of a aggressive stance, more of a defensive stance, more of a balanced stance, where they do a little bit more of aggressive. If the If the player appears weak, then the AI will attack the player and so on. Especially when a player has less armies or has a weaker kind of area than the AI does, right? So there's different strategies that you can imply for Risk or for chess. So really, strategy is really an approach used by some group of autonomous agents, and AI algorithms don't need to control necessarily one autonomous character, but maybe a whole set of characters. And then we can have decision making be influenced by the group strategy or pack tactics, if you will. For example, enemies can work as a team to surround and eliminate the player. That's like pack tactics. I want to kind of cut you off and all that kind of stuff. Can we get to this semester to create this kind of thing? We're talking about it. I think we're going to get close to it, but the goal of this course is not necessarily to create a strategy for your autonomous agents to surround the player. If we had another course in AI based after this one, I think this would be a great goal, to make your autonomous agents create a strategy to surround the player, right? We may not have time to do that this semester. I'm just pointing that out to you. Decision making, though, is something that we're definitely going to be able to do, and we're going to make decisions based on different structures, all right? And again, part of it based on what the AI senses. And I want to talk about this in general as well. We have something that could be, if you want to make a quote unquote fair AI, then we need to have the AI kind of sense the world, the game world, just like the human player would, right? However, we can also make an unfair AI. Unfair AI would be something like, I know the exact pixel location of the player. I know their exact location because I already know a lot about the player's position, so I can do a lot. But that's unfair, because in real life, if I have an enemy, they may not know my exact location. They can, if they see me, they see me. If they don't, they don't. If they hear me, they hear me. If they don't, they don't. But in games, you can give any information to the autonomous agent you want, which makes it unfair. A lot of times when we have the agent break the rules, mechanics of the game world, players get pretty upset, right? Like, wait a minute, how'd they know that we're going to be there? There's no way they can sense me or whatever, unless they have magic or some other kind of cameras or whatever. They can sense me in another room. There's no way they could hear me. My stealth level is super high, or I'm invisible, but somehow they can see me anyway, right? So we want to make it so that the decision making that is used in the AI in our games are based off of what the AI can sense, right? Again, these can be very simple decisions, and they can go very complex decisions based on the decision structures we create. And we'll talk about some of these. And some of these decision structures, we've already talked about. One of them is state machine. That's kind of a simple way. We can use something called a decision tree, which is kind of like a classification mechanism. We want to classify if the person is, or what kind of condition the player is in. Are they far? Or are they near? If they're far, do this. If they're near, do that. And then there's a behavior tree. And a behavior tree is more like, I have a sequence of behaviors that I can do. A good example of that would be, okay, I want to go into the room, right? We're going to talk about this later on this semester. I want to get into the room. Okay, cool. What do I do now? Well, I need to go to the door. Can I get to the door? Yes or no? Okay. If I can't get to the door, then how do I get around that? What do I do if I cannot get to the door? Like, I'm blocked somehow. There's like debris or something in front of me, right? Okay. And so there might be another set of behavior that I take, right? Based on if I can't get to the door. If I can get to the door, okay, cool. So is the door open? If the door is open, then go in, right? Again, these are a sequence of behaviors, right? If the door isn't open, is it locked? Can I unlock the door by picking it? Yes or no? If I can't unlock the door, if I don't have the key, or if I can't unlock it somehow, can I break down the door? Okay, if I break down the door, can I walk through? Or is there debris that's blocking my these are the things that you can do. Okay, if the door is is there's nothing I can do to get into the door. Maybe I can go and approach the window. Is there a way of getting into the room through a window, as an example? And these kinds of decisions are a sequence. They're in a sequence. So I do one thing, and the next thing is based on the previous thing. So if I'm successful in making the first action, then I can take the next action. That's different than a decision tree, which is basically like, okay, the player is far away. Okay, I move close to the player. Can I see the player? Yes, fire. I mean, it's like a lot simpler than perhaps a behavior tree. So movement is something that we're going to be talking about a lot, and because really one of the things that we're going to be talking about, especially in the first half of semester, is things like pathfinding. Okay, I want to find the closest path that my AI will take. Again, I've already seen the player, I can detect the player, right? I've heard the player, but I want to take the closest path to move towards the player. That's different. That is like, I want to use pathfinding. It's another type of AI, which we're going to talk about in the first half of semester. And actually, it's the first thing we're going to be talking about, pathfinding. Or actually, the second thing, steering behaviors is the first thing. But pathfinding is like, okay, so how can I calculate the closest path from me, my autonomous agent, to the player, around walls and everything else? Okay, that's what we're going to be talking about. And some of this is going to be unfair information that we're going to give the AI in order for them to figure out the closest path, right? Part of it also is knowledge of the world. Imagine if the AI knows where the door is. I know the location of the door that I'm in a room and I've got obstacles in the room and I want to get around the obstacles so I can go to the door. How do I do that? What's the closest path around the obstacles? When it comes to AI algorithms, that's really half the story. A lot of times what we do is we make these movement requests turn into actions. And what we want to do is we increasingly use things like physics simulations. And for physics simulations, we're not going to really cover a lot of this this semester. We're going to cover physics simulations next semester with physics. Okay, so that's something that we're going to be doing. We're going to be using the same assignment framework that we're giving you this semester to do that. Okay. A lot of times what we want to say is what we've been talking about, we've been running around this idea of AI sensing. Sometimes it's also called perception, where the autonomous character can see and hear the player. Okay. The other thing that you're going to hear a lot is something called agent-based AI. And whenever we talk about an agent, it can be viewed as anything that can perceive its environment through some kind of sensors, and it can act upon the environment through something called actuators. So again, human agents have things like sight, hearing, smell, taste, all this kind of stuff. A software agent receives some kind of keystrokes, maybe file content that they get, network packets, other kind of sensors that they're going to get in order for them to act in the game world. And usually it looks like something like this. It's kind of a funny picture that comes to the book, but I like this. Sensors, you might have some kind of sensing system or a sensing suite. As an example, the environment, it perceives the environment, and then it takes actions to act on the environment with its actuators, the way it can kind of move around the environment. Okay, so that is kind of the idea of an AI agent. Okay, and this is what we're going to be creating this semester, an AI agent. We can also use different kinds of performance measurements to make sure that it meets the AI agents meet requirements. Okay, so a lot of times what we have is we have a set of measurements that we want to make sure that the AI meets. Example, it's going to move at a certain rate. It's going to detect a player within a certain field of view distance. It's going to respond and it's going to blend its animations based on, and so on. And we can keep on talking about these things, but really what we want to be able to do is make it so that it is testable. Anything that we create from an AI perspective, we want to be able to test it and compare it versus things that we want it to do, right? The more testable an AI agent is, and we can apply measurements against it, the more we can debug it. Okay. So again, there's an idea called P's, right? Performance, environment, actuators, and sensors, right? P's. So again, we have a performance measure, right? Example, how fast is it? Is it good in the AI, the autonomous race car driver, as an example? The environment might be roads and weather. The actuators might be steering, acceleration, brakes, and tires, right? Does it come with potatoes? Sure. And the sensors would be things like the speedometer, the engine, other sensors outside the car, mirrors, all those kind of things are the things that the autonomous agent will use. Um, so, example, the task environment is the problem. The problem is roads and weather, which the rational agent will provide a solution for every frame. How do I navigate around a wet road? Well, I'm going to use my actuators, my steering, my acceleration, my brakes, and so on to do that. The car that it's driving, if you're playing a car race car kind of game. Again, just a reminder, algorithms are step-by-step processes, almost like a code block. And that code block provides some kind of data structure that holds data, as an example, that the algorithm can rapidly manipulate to reach a solution. Okay, that's what it is. Really, the efficiency, there's different kinds of efficiency that you can make the algorithm work, depending on how you code the algorithm. And if you take data structures at some point in your time here at George Brown, then you can figure out that there is an efficiency number. And the efficiency number in terms of big O notation is how efficient an algorithm is. You can actually measure the efficiency of an algorithm based on what you've asked it to do. We also do something called algorithm tuning. One of the things that I'm going to be talking about this semester is, and I'm going to say this a lot to you guys, make it work, then refactor. Okay, I think that's my motto in terms of coding. I make it work, and then I refactor. I don't try and refactor as I go. Guys, that's not a good practice, and girls, right? And people in general. The reason for this is because if we refactor as we go, we're never going to get things done. So when it comes to algorithm tuning, what we want to try and do is, does it work? How can we improve the algorithm, as an example, to improve efficiency and to reduce memory footprint? I think that's kind of the way we want to do things in this course. So what is good AI? We've talked about the history of AI. We've talked about a bunch of different things. Again, I like what it says here, which is when it comes to AI, bigger is not necessarily better. Good AI, it's got to feel good to the player. As an example, it's got to be realistic. It's got to provide challenge. I think these are important things. It's got to keep the player immersed in the game world. So when you're in the game world, you feel like you're in the game world. You don't have to think about that the AI is broken and we can defeat the AI. It's not about that. It's that that the AI that's presented by the game is somewhat realistic and provides a challenge. Okay. So again, I think this is really great where it says AI in games is a balance of hacks, heuristics, and algorithms. I think this is something that is true, and we'll focus on the algorithms, but it's also important to understand about hacks and heuristics. We'll be talking a little bit about heuristics in pathfinding, and we'll talk about what a heuristic is at that point in time, or actually more about that point in time. We're going to talk about a little bit what it is here. Hacks. We want the character to look right. Again, accurate representation of what they want them to be. We want simple gestures to convey emotion and those kind of things. Again, it doesn't necessarily have to be in 2D. We want to give the illusion of intelligence, but not necessarily intelligent. And what we want to also do is some kind of randomness. We want to add randomness to the AI so that it kind of feels like a regular random person. For example, think about the idle animation that you see in games. If it's completely repetitive over and over again, right? The idle animation is exactly the same all the time, right? And there's no variation. It breaks our immersion, doesn't it? Right? If it's too random, it also breaks our immersion. There has to be a type of pattern. And so what emerges for us is the ability for us to create profiles or personalities for each of our AIs. I like to call them loadouts as well. I make an AI loadout, and that loadout behaves in a certain way has a certain amount of efficiency and so on, and it can give us the illusion of realism, if you will. Heuristics is like a rule of thumb, right? It's usually some kind of approximate solution that might work in some situations, but not every situation. All right. So those are the things that we can use heuristics for, and we're going to talk about heuristics when it comes to pathfinding, different approaches to solve the problem. And sometimes when we talk about approaches to solve problems, you might think, as an example, that for example, there's a perfect solution, and there is, but sometimes it's not an efficient solution, right? It's perfectly, as you could perfectly find this thing in pathfinding, it'll find every possible path, but it might take a long time to do so. So we want to make an approximation. We want to kind of have a way of creating an algorithm that uses a heuristic to speed up and create something called AI that is good enough. And I think that's something that I want you to take away from this talk today. What is good enough from an AI perspective for your game? And what I mean by that is it's never going to be perfect, no matter what happens. It's like AI programmers are like artists in that way. When you start programming, you have to think about, as you're coding, can I continue? Can I make this more efficient and more efficient? Or do I want to move on? The more time you linger on a particular issue, as an example, may not necessarily make it better. Sometimes you actually step back and make it worse, right? So think about what is good enough and aim for that. So again, some common heuristics, the most constraints. So for example, we want the right tool for the right job, right? I like this one too. Do the most difficult thing first. That is definitely a heuristic. For example, an easy or simple action might be wasted. So it's usually basic to try the hardest action first, okay? Try the most promising things first too as well. One of the things I like to think about when it comes to common heuristics is get those low-hanging fruit off the tree first when it comes to trying to do what you want to do. And what I mean by that is, do the easy stuff. Get those, not just the difficult things, but get those things done. Like make it so that the ship moves around. It can detect the player. As an example, it can navigate around obstacles. Those basics, get those things working, and then and so that it looks realistic. And that's kind of tough to do. One thing to note also that is AI and hardware. Graphics technology has really, really improved. We know this. A lot of times what we're doing nowadays, especially with the latest graphics cards, I'm just going to use NVIDIA as an example, but AMD has very similar or comparable graphics cards that are out there these times. We can actually use or offload a lot of the calculations onto the GPU if we want to. And that's fine. We can do that. And when we offload things onto the GPU, we can use something called compute shaders as an example on the GPU to help us with AI decision making. Even when we do things like artificial intelligence, like deep learning and using neural networks, you can use the GPU to speed up your calculations, because we've got to think about that the CPU only has X number of cores, right? Where the GPU has thousands of cores potentially, right? So that's something that's happening, but not every game uses this, and not every computer, as an example, on a PC is built the same. So game creators, developers, they have an issue, right? How much do we want to offload our decision making onto the GPU? When there's a problem, it could be potentially that a person playing on a PC may not have a great GPU as someone else. So that's why they create controls to say, they can detect the GPU and its capabilities in order for you to increase efficiency and make the game play better. The other thing is, think about console versus PC versus handheld. Console is kind of a box, right? It's a closed kind of container. It's not going to change. Every console, if you play on a PS4 or a PS5, all PS5s are pretty much the same. All PS4s are almost exactly the same, right? All PCs are not the same, right? And so when it comes to making games for a particular piece of hardware, from a hardware target perspective, then yeah, targeting consoles are easier. But we've seen examples. Here's some examples lately of games that have failed when it comes to meeting hardware requirements. Can anyone think of a game lately that has failed in hardware requirements to work across different platforms? Anybody? Cyberpunk, yeah, that's the first one I thought about too. Cyberpunk 2077. They went crazy and created a game that was supposed to work on all platforms, but it kind of worked on PC with some glitches, did not work well on console at all, and not handheld, that's for sure, right? So, and again, we can learn from games like Valheim, which is a very simple game that was made by a group of 5 programmers, 5 developers. It was made with Unity, which is really cool. And they only made it for the PC. It's not available on a console or handheld device. Will it be in the future? I guarantee it. It's going to be made because that's how popular it is. Is it ready to port to a console or to a handheld device? No, it's not. Not yet. And these guys did it right. They programmed it well for PC. They have one release. They're still in early access, and they're probably not going to do anything until the game is completed. When the game is completed and it's ready to go, they can port it to console. Now, we know that Unity is a multi-platform game engine, just like Unreal. So is it that difficult to make a game that works on a console compared to PC? No, but there are definitely some changes to be made for the console port. So that's the thing that I think Cyberpunk did wrong. And why am I talking about this? Because if we think about it, and if we keep it simple, if you target one platform, whatever it is, and this is kind of a lesson that we've learned from a hardware perspective, target one platform, do it well, and then you move on to the next one. All right, so that is that is a little bit of a conversation about AI. What is it? What are our goals for today, and so on. What I'm going to do now is I'm going to stop recording this video, and then I want to talk about the assignment that is going to be due in 2 weeks from now. Okay, so I want to talk about this now. So I'm going to stop recording the video on YouTube, and then I'm going to create a new one, and I'll share that with you guys, and it's all going to be around assignment 1. All right, so I've stopped.